Very quickly, in our last session, we started looking at how we would estimate the coefficients beta naught hat, or how we would calculate, right? They themselves are an estimate. Beta naught hat and beta 1 hat. We're not using least squares. That would require numerical data and a linear model. Instead, we're using this lowercase l function. Lowercase l, that's the likelihood function. And what is p of xi? Well, I would imagine it's this, but you substitute. So for each observation, you plug in the characteristics of that observation. And in this case, we're only working with a single predictor variable, the balance on each borrower's credit card. And once you plug it in, for every beta naught and beta 1, you can create, or you can calculate the likelihood. So likelihood is a function of beta naught and beta 1. We're going to maximize, so we're going to, please think of it as selecting those two parameters for which the likelihood is maximum. So it's no longer minimizing the residual sum of squares. It's maximizing the likelihood. How's the likelihood calculated? We have these uppercase letter pi, that's for product. It's in the same way that you have uppercase sigma for summation. And you multiply, and remember, when you multiply, can we call this a probability? It is a probability, right? This is each probability of, I think when y is 1, that's default. Remember, default is just when the borrower, okay, there are many variations, but let's just say doesn't pay his or her debts. Now that comes in different variations. Have they just fallen behind, or are they going to pay over a longer period of time? But just think of it as the bank has a problem. The bank has a problem with anyone in the data set whose y variable, the y variable that we're trying to predict as a function of certain borrower characteristics, balance, income, whether a student or otherwise, you multiply each of these probabilities. In the data set, I think it's 333 of them, and the remaining 9,600, these are the probability of no default. Now, so what are we saying? We're saying that for every beta naught and beta 1, this function will give you a different output, but we pick beta naught and beta 1 that maximize this output. In fact, that's exactly what we're saying here. The estimates beta naught hat and beta 1 hat are chosen to maximize this likelihood function. Maximum likelihood is a very general approach that is used to fit many of the nonlinear models that we examine throughout this book. In the linear regression setting, the least squares approach is in fact a special case, yeah, of maximum likelihood. The mathematical details of maximum likelihood are beyond the scope of this book. And that reminds me, I definitely have a document somewhere, although I don't spend too much time looking for it, where I actually did try at one point. I may have saved it in my R folder. So I realize this is a bit of a dead spot, but it might be worth just a couple of seconds. Would it be in my documents? Would it be in R? Maybe R Studio? Would I have saved it over here? I need a Word file. So I can't seem to. Just bear with me. What if I do? What's the book called? I was looking at another book. And did I not save? Maybe I didn't even save the document, but at one point, yeah, I'll try finding it at some point. I doubt it's in my downloads. It would be a strange place to. Never mind, never mind. What I was looking for was that at one point I had filled out quite a lot of the details when it comes to logistic regression, which is what we're doing over here. We're using an expression of this type. And I've actually filled in quite a lot of the details as to how you would estimate beta naught and beta 1. There's definitely differentiation. There's also logs as well. What we normally do is instead of maximizing the likelihood function, we maximize the log likelihood function. Because it just makes things easier, but you get the same answer in any case. The book is saying the mathematical details of maximum likelihood are beyond the scope of this book. However, in general, logistic regression and other models can be easily fit using a statistical software package such as R, and so we do not need to concern ourselves with the details of the maximum likelihood fitting procedure. We can do it at a later stage if I find my own personal notes. Table 4.1, very familiar layout. If we go back to chapter 3, shows the coefficient estimates and related information that result from fitting a logistic regression model on the default data in order to predict the probability of default equals yes using balance. We see that beta 1 hat is equal to 0.0055. This indicates that an increase in balance is associated with an increase in the probability of default. So it's, what we're saying is that it's positive. Now, to be precise, a 1 unit increase in balance is associated with an increase in the log odds of default. You need to apply log. There is linearity, but there's only linearity when we write the relationship as log odds against your predictor variable, against the balance. And if beta 1 is 0. However many zeros, 55, increasing x by 1 would increase the pink by beta 1. Now, of course, that's just an estimate. That's just an estimate. And you could say that's so close to 0. Now, of course, such a statement on its own is just something you seem to be saying it practically every one of these meetings, but close to 0 means nothing. There's no such thing as, you can speak about closer to 0. Of course, 1 is closer to 0 than 2 is. So we need to kind of scale it by something that puts things into context. And what puts things into context? The standard error. Now you can look at the relative size of these two coefficients. Many aspects of logistic regression, or of the logistic regression output shown in table 4.1, are similar to the linear regression output of chapter 3. For example, we can measure the accuracy of the coefficient estimates by computing their standard errors. The Z statistic in table 4.1 plays the same role as the T statistic in the linear regression output. For example, in table 3.1, for instance, the Z statistic associated with beta 1 is equal to, and it's the same thing as in chapter 3, where you divide the blue by the pink. I said pink. And that's what's giving you the 24.9. And this is where we say you get such a low p-value for this. By the way, Z statistic, I think that's the, usually when you see Z in data science, it's the normal distribution, the standard normal distribution. Why aren't I just doing this in Desmos? Yeah, beats me. And what we're saying is 24.9, it's really, really unlikely. You're going to expect most of your values to be, I don't know, between, for example, -2 and 2. I think that captures like, you have like, I think it's like 96% that, whereas this is 24.9, which is, it's way out of that sort of mainstream interval. And so a large absolute value of the Z statistic indicates evidence against the null hypothesis. Null hypothesis is that there is actually no relationship between default and balance. This null hypothesis, so the null hypothesis, it would give you no term with X. It will give you no term with X. So the null hypothesis is telling you the probability of default does not depend on balance. Since the p-value associated with balance in table 4.1 is tiny, we can reject H0. In other words, we conclude that there is indeed an association. That's always your first step, right? In building any model, you should be including predictor variables, X variables that actually have some impact, a statistically significant impact on the response. It's pointless, you're predicting, we often say predicting the performance of students in a specific exam, and one of your input variables, one of your predictor variables is what can I think of? Is it raining on the day of the exam? Yeah, it might affect 1 or 2 students out of maybe 100 or 10,000. Maybe they arrive late to the exam, but it's so statistically, or you would expect. I mean, you could test it, which is what we're doing over here. But your model is going to exclude many more predictive variables than it's going to include. In other words, we conclude that there is indeed an association between balance and probability of default. The estimated intercept in table 4.1 is typically not of interest. Its main purpose is to adjust the average fitted probabilities to the proportion of ones in the data. I guess it's not too important. Okay, now, this is where maybe it gets a bit more mathematical and maybe a bit, there's more to as hopefully extends our understanding. Let's have a look. We have a practical example. Once the coefficients have been estimated, and we saw earlier that our coefficients are beta naught hat and beta 1 hat, it is a simple matter to compute the probability of default for any given credit card balance. So any given credit card balance. So we're taking, for example, $1,000, and we're going to calculate the probability of default. So this means probability of default given. So maybe all of this should be in yellow, right? What is, and see the hat, of course, this is just an estimate. We'll probably speak of confidence intervals at some point. P hat, excuse me, of X. For example, using the coefficient estimates given in table 4.1, we predict that the default probability for an individual with a balance of $1,000 is, and we'll take the book's word on it, 0.00576, which is below 1%. In contrast, and notice this is where nonlinearity comes into play. In contrast, if the balance is double, and I don't think I've used orange yet, if the balance is double, the probability does not double, but it in fact increases by 2 orders of magnitude, right? We've dropped these zeros, so it's increased by it's 100 times more likely. Really, really insightful, isn't it? Because linearity, while useful, most models break down. And I will keep on mentioning Hooke's law for those of you who had, as probably one of your first experiments in physics, that's where the material that you're stretching, some kind of metal, you name it, once you hit, I'm not sure if it was the limit of elasticity, or is that when the object doesn't return to its original state. Anyway, there comes a point where the linearity assumption breaks down. Over here, the great thing about our model is it's not assuming linearity in the first place. You will get maybe parts of the model which sort of over a specific. So look, this is exactly what we're doing right now, right? I would imagine the numbers. So a balance of 1,000, and what the model is giving you is nearly a 0 probability, whereas 2,000, well, that's your 58 point whatever percent. There are moments of linearity. I mean, for example, this part over here, over this specific interval, it can feel very linear, but of course, comparing them, it's definitely not linear. Look how badly this line approximates the actual model. These are all really important concepts, and wanting something to be linear, but very often having to accept that the assumption just doesn't make sense. Which is why we are doing chapter 4. One can use qualitative predictors. Okay, and that's fun. One can use qualitative predictors with the logistic regression model using the dummy variable approach from section 3.3.1. As an example, the default data set contains the qualitative variable student. To fit the model, we simply create a dummy variable that takes on a value of 1 for students and 0 for non-students. The logistic regression model that results from predicting probability of default from student status can be seen in 4.2. So now we're only looking at we should start seeing how we could actually create these tables in R, right? I suppose that will be covered in the lab section of the chapter, which is usually towards the end. So the coefficient associated with the dummy variable is positive. So that means if you are a student, you're more likely, I think. Again, if P is low, what was it? If P is low, H naught goes home. No. If do you remember the phrase? If P is low, then H naught must go. And the associated p-value is statistically significant. This indicates that students tend to have higher default probabilities than non-students. Now, what's interesting is this. Would you not expect these two probabilities? I clearly have the wrong interpretation of it, but wouldn't you expect these two probabilities to add up to 1? Default equals yes, given student equals yes. Default equals yes, given student equals no. And there are no other options, right? So, but the book doesn't comment. That's interesting. So how are we saying if you are a student, you have a 4.3% chance of defaulting? If you're not a student, 2.9. Wouldn't you expect these two to add up to 1? No, of course not. What on earth am I saying? That's a very, 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 very stupid thing of me that I've said. This is probability default equals yes. And if you subtract this from 1, then you have default equals no. Yeah, I was clearly thinking of this in the wrong way. Multiple logistic regression. Notice the parallels with the way we set up linear regression in the previous chapter. We now consider the problem of predicting a binary response using multiple predictors. By analogy, with the extension from simple to multiple linear regression in chapter 3, we can generalize 4.4 as follows. Yep, where X, let's make this clear, This is a vector now. It's a vector with 2 or more components, multiple, not simple, not singular. Just as in section 4.3.2, we use the maximum likelihood method to estimate all these parameters. Table 4.3 shows the coefficient estimates for a logistic regression model that uses, so referring to this chapter, you have 2 numerical and 1 is qualitative. So you see bracket CS, that means that we're using dummy variables and we're just saying 1 if yes, 0 if no, yes student, no student. There is a surprising result here. The p-values associated with balance and the dummy variable for student status are very small. So these are we should really highlight them, yeah. So these are very small. But income, it's certainly not small, right? No, what do we normally mean by small? Well, it depends at which confidence interval you're working at. But normally it would be, for example, less than, less than 5%. Whereas this one's 71%, so it's a lot larger. And maybe we were expecting this because if you look at income, the profiles weren't too different. If you look at the median of each one, for all those who defaulted, beg your pardon, the blue is those who did not default, and these who did default. So this is probably what we're getting at over here. However, the coefficient for the dummy variable is negative. Oh, interesting. This time around, it's negative. Indicating that students are less likely to default than non-students. In contrast, the coefficient for the dummy variable is positive in table 4.2, which is what we had over here. So are we, I know, I'm kind of going from one page to another. This is a positive coefficient for a student. This is negative. If I had to guess, we're probably going to put more trust in the negative. This might be totally off, but given that we're, it's like multiple linear regression. Let's see. How is it possible for student status to be associated with an increase in probability of default in table 4.2 and a decrease in probability of default in table 4.3? The left-hand panel of figure 4.3, figure here. So this is the left-hand panel. Is this it? Is this left? Oh, my connection is unstable. Let's see. I am still connected, aren't I? Okay. Let me know if there are issues. So the left-hand panel of figure 4.3 provides a graphical. Okay. Okay, so if I don't know if I don't think we need to repeat anything because I was just looking for a diagram. But thank you for your comment. The left-hand panel, figure 4.3, provides a graphical illustration of this apparent paradox. The orange and blue solid lines show the average default rates for students and non-students respectively. Let's have a look. So orange, that's a bit irritating. Are they using, we were earlier using orange and blue for default, not default. But now we're looking at, let me just see. So blue is non-students. This is non-students. This is how non-students sort of, as the credit card balance increases, how many of them defaulted. So take all the students. Blue is non, right? Blue is non-students. The non-students, blue. Take all the non-students that had a balance of 2,000. So many of them defaulted. Now take all the students that had a balance of 2000 as well. Only so many of these defaulted. So the thing is, in a multiple regression model, we're kind of getting more information. And we're not just looking at if the student defaulted or did not default, but we're also looking at for which balances the student defaulted. But let's see if the book does a better job. Yeah. So let's take a step back and go over this properly. The orange and blue solid lines show the average default rates for students and non-students respectively as a function of credit card balance, Look, the dotted line shows you the overall rate. So while it is true that more students did default again when compared to non-students, while the orange is higher than the blue over here it's sort of the other way around, isn't it? That when you include credit card balance, the blue, which is the non-students, is actually higher than the orange. The negative coefficient for student, this negative, the negative coefficient for student in the multiple logistic regression indicates that for a fixed value of balance and income, right? You kind of think of it like sort of like partial derivatives, where you're keeping all variables fixed with the exception of one of them. So for a specific balance and income, just pick anything, pick a balance of 1,000, pick an income of $10,000. A student is less likely to default than a non-student. So this is the power of using multiple variables, that actually you're getting this really good insight into what probability of default to expect between students and non-students, given a specific balance and given a specific income. By specific, I mean fixed. Indeed, we observe from the left-hand panel of figure 4.3, the left-hand panel, that the student default rate is at or below that of the non-student default rate for every value of balance. The orange is less than the blue for every value of the orange, for every value of credit card balance. But the horizontal broken line near the base of the plot, which showed the default rates for students and non-students averaged over all values of balance and income, suggests the opposite effect. The overall student default rate is higher than the non-student default rate. Consequently, there is a positive coefficient for student in the single variable logistic regression. Be interesting to see this in R. What am I referring to? Is there a way that we can see how many students defaulted? How many students defaulted I'm not entirely sure I know how to do that. So what I'm saying is I only want to pick. So this is your data set, or at least the first 6 observations from around, yeah, I think it's 10,000, right? How would you only pick those observations that say student yes? Let's see. Is there a way where you can say, I think I'm going to have to look into what if you say student, double equals yes. So that doesn't work. I'm not surprised. After all, student is a column. So what if you say this? Any row? No, more like this, right? And that unfortunately doesn't work either. So it's not something I necessarily know how to do right now. I have done it in the past, which that doesn't really help anyone. What if you, so this is just one vector, and what if you say, okay, so that kind of is doing something, isn't it? It's telling you true, false, saying which ones are students. And what other data did we have? We had default, right? Default is just, so what if you do, so if, I know I'm not doing a good job of explaining this, but what I've done is, this is definitely a shorter way. What I've done is, I've taken over here just the student data. Yes, student, no student, and said yes. So what R does, it gives you a vector where it tells you the first observation is not a student. The second observation is a student. What you could do, and again, there's a definitely not a very elegant way of doing it, but when you have these two vectors, you can now sort of multiply them. That's a kind of the and, you're saying, let me just, so for example, let me just, X and Y. Well, what I'm doing over here is I'm saying, okay, the second observation is a student, true. And then over here, the second student did not default. And if you want to know which of the observations are both a student and a defaulter, you can sort of do X times Y. It kind of works out like and. If you've ever seen logic tables, it's true from and you only get a true statement if you give it two true statements. So if I do now this and I sum, there's 1, 2, 7. I know it's a very convoluted way of doing it, but these are in actual fact all those observations that are student yes and default yes. So for example, our first student who defaulted is this one over here. So right about, I don't know, like maybe the 130th observation. Again, it's a very long way of doing it. It works, it definitely works, but there's no way you would actually want to implement any code in such a manner. Okay. We could also look at, what if we do Z and we say no, and we say sum of Z times Y. So these are the non-students. So the non-students did default more than the students. If you want to look at it as a ratio, it's not quite twice as many, but 0.0127, these are the students. 0.0, so you get like 1% and 2%. And that's what we have, these two lines. The blue is that right? Yeah, exactly. The blue is 1% default. The orange line is 2% default. But in actual fact, when you then allow for example, credit card balance, for a given credit card balance, you actually have blue is always higher than orange. Now in practice, you get some parts where you know, in general, you won't get one curve which is always greater than the other curve. The book specifically created this data to give us maybe the extreme cases, and then in practice you get everything in between. But hopefully that helps explain why this is negative in the multiple linear regression and positive in the simple logistic regression. We're going to ignore this. We're going to, there's no way that we're only going to look at whether a person is a student or not to make our predictions. Can you imagine? Can you imagine going to a bank and the one thing they ask you is, are you a student? In fact, if the only one thing they ask you is a student, besides not being a good model, that could easily be construed as a discriminatory practice, right? They're only looking at one aspect of yours, number one, and two, also legislation. Legislation might, there's some very, very clearly defined characteristics that you are not allowed to use. You can't use the race of a person. With the EU, there's a gender directive. It's only come into very, very, very recently. We were saying maybe last 5 years. And you may have heard of insurance companies which their gimmick was that they would only sell insurance to women, or they had maybe a specific product which would only target women, because women are not better. Who cares about better? But women statistically cause less losses for insurers. Let's put it that way. And with one consequence of the gender directive is that as an insurance company, you can no longer offer different rates to men and women. You based on Now, of course, you could do it indirectly, and that's something else that you really need to watch out. You need to watch out that your model. So if you think about it, it's quite funny, or at least I think there is there is the funny side to it that your model could be breaking the law. Your model could be going against just the just you know laws, regulations, directives that models can also be very good, even though you don't tell them that a person is a man or a woman. You can pick out other characteristics that give you a very good idea. If I mean, the first thing that comes to my mind is not that insurance companies are doing this, but first thing that comes to my mind is hobbies, right? That there are quite some significant differences. Now, is it the way we're socialized? Is there something different in our brains? Who knows? Who cares? Would be probably one good answer. But if does the policyholder have, or does the prospective borrower have a hunting license? Uh, just to take an example again. Well, if you know that they have a hunting license, I think you can make a very, very good estimate if that person is a man or a woman. In terms of student as well, does the person have a driver's license? In our country, if the person doesn't have a driver's license, then probably they are still a first year or second year student. There's a very, very interesting article by, I think we can go into my browser for a second. If I have a browser open, and it's the usual suspects, Woodrich or Woodrich. Really need to meet this person one of these days. Gender, actuarial, EU directive, model, unisex stochastic mortality model to comply with. Yeah, these are all. But let me type. It was a very good article. It was the cover page article. In fact, it was the featured one. Actuaries, or the actuary, I think, actuary. Hmm. Hmm. Let's have a look. Hmm. The Actuary magazine, EU gender directive model. I'm surprised it doesn't come up because this was, like I said, meant to be like it was the feature. I think it was the feature article of that month. Now, is this my fault for not using Google? Anyway, if we look at the research paper, can we download it, or do I need an account? I feel like creating one right now, but if we had to look at the graphs, which do look freely available, we're doing something very similar in the book, aren't we? All these dotted lines, and well, it's not saying much, is it? And it's just a chart. But But this is what I mean by discrimination and having your model not implicitly. What if I typed implicit discrimination? Implicit discrimination in actuarial models. Actuarial group takes steps to identify racial bias in insurance rates. As the insurance industry grapples with potential racial bias in the pricing of insurance products, in the age of artificial intelligence and modeling, a group of property casualty actuaries, so this would be non-life, have issued two new research reports to help guide the insurance industry away from discriminatory effects. Higher insurance, was that from the discriminatory effects? Higher insurance pricing for Black people and others of color. More specific, yeah, so here we go. See, let's see, probably geographical location would be one of them, where if a society was still quite segregated. Four rating factors, and what are the four rating factors? Age might be another one. If you know they certain racial groups tend to be on average younger than other racial groups. Um, I'm pretty curious now. Oh, by the way, when you see FCAS, that means a Fellow of the Casualty Actuarial Society. So think of the UK's FIA, but Casualty Actuarial Society. So what are they? What are they? Oh, okay. So credit-based insurance scores, geographical location, clearly right. Just think of sociological behavior known as, for example, gentrification, that when a specific area starts to sort of become more affluent, where maybe the original inhabitants get priced out of the rental market. Think of another phenomenon known as white flight. Think of ghettoization would be another thing that comes to my mind. Oh, yeah, home ownership, right? Where, for example, in the US, most wealth is generational. You inherit your parents' property, their maybe their residential home. It goes up in value. You sell it. When you sell it, you can take out a mortgage. Home ownership is another big one, right? Another major difference between different races. And motor vehicle records. This would seem to be the fourth one. Nothing else, right? Yeah, and then moving forward. These are some really interesting papers. And this is something that maybe in the US they maybe there's more focus on sort of social justice, which I think we should all be for. Very interesting. So you're seeing how actuaries are having an impact on just people's lives, really, right? Your model, the outputs of your model, they do impact people. Uh, Over here, we're like looking at, for example, the affordability of insurance. The problem of implicit discrimination among people of color, those in poverty, anti-discrimination, insurance pricing, regulations, fairness criteria, and models. Yeah, so I mean, there's so much out there. What is implicit discrimination? So we didn't quite find the article I was after, but I still think what we read now right now is probably quite interesting. Or I hope it was interesting. A student is riskier than a non-student if no information about the student's credit card balance is available. However, that student is less risky than a non-student with the same credit card balance. This is such a beautiful example. This simple example illustrates the dangers and subtleties associated with performing regressions involving only a single predictor when other predictors may also be relevant. As in the linear regression setting, the results obtained using one predictor may be quite different from those obtained using multiple predictors, especially when there is correlation among the predictors. In general, this phenomenon, seen in figure 4.3, is known as confounding. Now what's this? Student status and credit card balance. I don't know what that is. So by substituting estimates for the regression coefficients from table 4.3, so these three, 0.0057 until negative 0.64, let's highlight them in pink. We can now estimate the probability of default given this vector. And this vector is going to be what? It's going to be a credit card balance of 1,500 and an income of 40. So I think this is measured in thousands. And a student. So this specific model now is looking at three predictor variables. So it needs three inputs to make any predictions. And imagine you're the bank manager, and there is a this client in front of you. She is a student. She has a credit card balance of 1,500. She has an income of 40,000. What is the probability that she defaults? Well, the model seems to be suggesting that the probability is just under 6%. Then obviously it's a management decision whether to grant her the loan, what the interest rate is going to be, how much you're going to lend her. And it's not just yes, no, right? It's not just a case of you're going to give the loan, or you're going to lend, or you're going to issue the loan, or you're not going to issue the loan. A non-student with the same balance and income has an estimated probability of default of, well, now it's nearly double. So it's the same inputs, credit card balance of 1,500, annual salary of 40K, but now it's 0, and now it's 10%. And as you would expect, in actual fact, students are less risky for a given, and that's always what you're doing, right? When you have someone in front of you for a given credit card balance, for a given income. So here we multiply the income coefficient estimate from table 4.3 by 40. Yep. So the model is measuring in the model is measuring in thousands. So I think we can think of wrapping up. We'll look next time we meet. We'll look at maybe we'll do it Sunday. We'll probably skip tomorrow's logistic regression for more than. But let me confirm. Logistic regression for more than two response classes. And something called linear discriminant analysis. Don't ask me what it is. Oh, cool. Oh, is this? Oh, this is where it's going to get really interesting. Where we're going to use instead of we've been using, for example, normal. It shouldn't do that over there. Normal distributions or F distributions. This is where I'm going to kind of rotate it 360 degrees, and it's going to be the probability if for given x1 is a value and x2 is a value. Oh, nice. Okay, so there's a lot to do, but we're definitely getting there. We'll stop this here.